Hello, my name is Ziran Jiang from Dr. Chan's research group in the chemistry department. Today I'm going to talk about the second generation synthesis towards a macrocyclic ketone mimic of Zampanolide. I will give you a brief introduction of prostate cancer, and I will talk about the Zampanolide compound and its mechanism of action. And I will talk about the objectives and the results of the project. At the end, I will wrap it up in the conclusion section. In 2020, 1 in 9 American men will be diagnosed with prostate cancer, and it's got the highest incidence rate amongst other cancers. Due to multidrug resistance mechanisms in prostate cancer, it's been estimated that 33,000 US men will die from prostate cancer. And prostate cancer is the second most lethal cancer in US men, and of course, we are in an urgent need of finding new treatment. In the search of new treatment, in 1996, scientists like Tanaka and Higa were able to isolate Zampanolide from a marine sponge called Phaseospongia remosa. It was collected off Cape Zampa in Japan in a yield of 0.001% from 480 grams of the marine sponge. And why were they interested in Zampanolide? Zampanolide was able to show low nanomolar level anti-proliferative activities against different cancer cell lines. So IC50 value was used to measure the activity. IC50 value is the concentration that the compound needs to suppress half of the cancer cell lines. So the lower, the better. So both compounds, Zampanolide and paclitaxel, which is a FDA-approved anti-cancer drug, and they both show really low nanomolar IC50 value against this ovarian cancer cell line. However, when they tested these two compounds against a multidrug resistant ovarian cancer cell line, paclitaxel needed a lot higher concentration to suppress half of the cancer cells, but Zampanolide showed similar IC50 values throughout 3 different cell lines, including the multidrug resistant ovarian cancer cell lines and PC3, which is a prostate cancer cell line. So how does Zampanolide works? Same as paclitaxel, Zampanolide is a microtubule stabilizing agent called MSA, and it's been shown to be able to disrupt the dynamic instability of microtubule, which is really important for mitosis. After Zampanolide binds to the microtubule cannot work properly during the mitosis stage, and that's going to lead to apoptosis. So the second mechanism is that MSA can also disrupt the androgen receptor trafficking mechanism to suppress prostate cancer cell growth. But what's unique about Zampanolide is that the carbon 9 of Zampanolide can bind to histidine 229 of microtubule using a covalent binding. So this covalent binding is really important for Zampanolide to evade the overexpressed efflux proteins in multidrug resistant prostate cancer. But so right now we know that all the good things about Zampanolide. Why don't we put it to in vivo study? So we actually envisioned that the lactone moiety of Zampanolide is not stable enough in vivo. We have a lot of non-specific esterases in our body that are able to digest this ester group, and after you digest it, Zampanolide is not going to be active anymore. And another problem is that in vivo study needs a lot of the compound in grams, so the THP ring of Zampanolide is synthetically impractical. And if you want to extract this compound from marine sponge, remember we only got 0.001% yield from the marine sponge, so it's impossible to go from there. So we planned to stabilize the structure by replacing the ester group into a ketone group, and then we try to simplify this moiety by eliminating the THP ring as well as 2 chiral centers to have this simple ether right here. So since the enantiomer reagent for the synthesis is too expensive, we try to use the racemic mixture of it to find our way to synthesize this core 6 structure first, and then in the future we use the same method, but the enantiopure reagents to synthesize our enantiopure final structure. So to close the macrocyclic ketone ring, in the first generation synthesis, we used HWE reaction, and then Williamson ether synthesis was used to attach fragment 9 through 11 to here to form the ether moiety. To merge two major fragments, we used a HWE reaction, and then the construction of the carbon bridge between carbon 17 and carbon 1 was accomplished through a carbon 1 catalyzed cross-coupling reaction. And to alkylate these two little fragments, we used an epoxide ring opening reaction. So we were able to get to this point having only 80 milligrams of the intermediate, and we tried to attach the fragment 9 through 11 at this point, but we tried 4 different methods. They all failed. So I was thinking that would it be a little bit too late in the synthesis stage to attach this fragment? Because if we fail, we need to resynthesize everything all over again. So we attached the fragment a little bit earlier. So in our second generation synthesis, this connection was similar, except that the fragment 9 through 11 was attached to a compound that is in a really early stage, and this is the only difference in the second generation synthesis. To start, we start with 2-butyl-1-ol. It went through a regio and stereo selective hydrostenylation to attach tributylene right here for the iodination right here. It gave pretty nice yield right here. And after that, we try to form the ether here through a Williamson ether synthesis. Of course, we have to turn this alcohol into a tosylate. And then without purification, we moved on to the ether synthesis mediated with sodium hydride, giving 60% yield. And after that, we try to construct our compound 22 using a lithium halogen exchange reaction mediated by terbital lithium, generating the vinyl nucleophile to attack the epoxide ring right here. So right now we have our carbon 9 through 17 constructed. Without purification, we moved on to the next step, which is the tosylation of the secondary alcohol right here. It gave us a 40% two-step yield. And then after tosylation, we were able to use this tosylate to for our carbon 1 catalyzed cross-coupling reaction, giving 40% yield. So right now we have the construction of carbon bridge between carbon 1 and carbon 17 done. So after that, we used a B2-pin2, which is a really bulky diborane group, to selectively diborylate the terminal alkene. And then after that, we used hydrogen peroxide to do the dihydroxylation of the diborane group. And then after that, we needed to generate a leaving group in order to form our epoxide using pyridine and mesylate chloride. And after we have the mesylate, we used a sodium hydride as a base to form our epoxide, giving really high yield. After that, to construct our HWE precursor, we opened the epoxide ring using a diethyl phosphide group. So after that, with that attached, we used a DMP, which is the Des-Martin periodinane, to oxidize the secondary alcohol into a ketone. And then after that, we merged two fragments using the HWE reaction. So right now we have a really important intermediate right here. So to close the ring, we planned to use a HWE reaction. We did the deprotection of two TBS groups, and it gave us a 37% yield, two-step. So we used a concentrated hydrofluoric acid in pyridine complex. And after that, we were able to get 20 milligrams only. After 24 total steps and 15 linear steps, it took me almost like 2 months. It was like definitely more than 1 month to synthesize this intermediate. And after that, we tried so many times to synthesize this compound right here. We are still 1, 2, 3, 4 steps away from the final compound. So in conclusion, we successfully constructed the carbon bridge between carbon 17 and carbon 1 via a carbon 1 catalyzed cross-coupling reaction, and we merged 2 major fragments through an HWE reaction, and we achieved a highly advanced key intermediate through 15 linear step synthesis. In the future, we want to synthesize the complete core structure, core 6 structure, and test the bioactivity of it. I would like to thank Dr. Chen, Mr. Chen, and our research group, and also chemistry department. They offered a lot of help, and we need to thank NIH for the funding. And thank you.